Ladies and gentlemen, welcome to my lecture on problems with statistical tests in empirical research. First of all, what are the requirements for this course? So this course is not for undergraduate students, so it's for graduate students and PhD students. So what I expect that you have a sound knowledge in econometrics or statistics, that you know basic mathematics, like including matrix calculus especially. And of course, the basic theory of stochastics. So all of these are tools that we in this lecture employ. So why is it important? Well, in any social science, you have a theory and you would like to test the theory in order to either to validate it or to reject it. So you have a theory, then you do the empirics, and for empirical research we operate with statistical tests, right, in order to either to accept the theory or to reject the theory. Once we reject a theory, we build up a new theory, an improved theory, and we do the same thing over again. So empirical tests are obviously very important, and you will need these kind of procedures in any kind of social science. So what's the problem in social science in general? So according to research, if you just consider financial economics as a research discipline in social science, research has shown that about 80% of published results fail scientific replication. 80%. So what about other disciplines in social science? What about, for instance, psychology? Let us listen to Dr. John Peterson, who is professor of psychology at the University of Toronto. And he will tell us how it looks like in research related to psychology.
And it's really important because insofar as you guys are interested in psychology, especially in the experimental end of psychology, measurement is everything. And so much of what psychologists publish and write about is incorrect. And the reason it's incorrect is because they do not have their measurements properly instantiated. It's a massive problem, especially in social psychology. In fact, it's probably a fatal problem in that most of the things that social psychologists measure don't exist. And social psychology has been rife with scandals for the last 4 or 5 years. And there's good reason for it. But a big part of the problem is that the measurement, that people are not stringent and careful enough about their measurement.
So obviously we face the same problems also in other disciplines. It's not only a problem that is specifically related to research in financial economics. So which brings us to the data. So what's the problem with the data? So obviously we have often dependency structures in the data, different types of dependency structures. And for an example, for instance, in financial economics, what we often see is we have a clustering in the return distribution, just as an example. So let's have the the observations of the returns here on the x-axis, and here we have the return at time t. So what we often see in finance, that the return distribution looks like this. So we have a low volatility, and then all of a sudden we have a state or a regime where the volatility is very high. Then again, it goes back to normal levels, or what is normal? It goes back to lower levels, and then at some point we see again a higher volatility. And then it goes back to lower levels of volatility over a certain time period. So this is a stylized fact of financial markets, and we see this in any financial market, not only in stock markets. We observe the same patterns in cryptocurrency markets especially, or in commodity markets, or in currencies, in traditional currencies. So this is called volatility clustering. So it obviously concerns the second moment, right? So it's called volatility. clustering. And this is just one problem. So another thing that we observe in financial markets, for instance, let's see here, let's again take a plot in order to visualize it. So again, on the t-axis, we plot the return across time of some asset. Yeah? So what we also sometimes observe is that we have a certain regime, yeah? A certain time period where the return distribution has, let's say, a return of minus r bar, and then after some time it switches, yeah, and the return distribution goes from minus r bar to plus r bar. Yeah? And then after some time the return distribution falls below. So when we are again here in the state where we have the return of minus r bar for a certain time period, and then all of a sudden it jumps back and it generates returns that are in line with plus r bar. Yeah? So you might have heard about bull and bear markets. Yeah? So this goes a little bit in this direction. So we have a regime switch. Yeah? A regime switch. And in practical terms, people sometimes refer this to bull and bear. Yeah? So we have obviously a regime where the expected return or the sample average return is depending on a certain time period, and it's below a certain level, and then it switches and goes to above a certain level. Yeah? So the average return is then obviously somewhere here in the middle. Yeah? So while this concerns the first moment, yeah, the sample average is switching, this guy here, the volatility clustering, concerns the second moment, yeah, obviously. So the sample average here is always the same. Yeah? It's just the uncertainty around this sample average that is obviously time dependent. So, and we can also observe sometimes both at the same time. So then things become even more complicated. So obviously, what we see in data, or empirical data, we have obviously different types of dependency structures. And what we usually would like to see, and our models, or mostly the models used in social science, they rest upon the assumption that the data is well behaving. So what we would like to see is that data is something like that, that it's well behaving. Yeah? So we don't have this clustering, it's somewhere moving around, well behaving. And you might have heard about the normal distribution. So what is often assumed when models are derived, or when we perform empirical tests or statistical tests, what is often assumed is that data is distributed as normal, yeah? With zero mean, or with some mean, let's call it mu, in order to make it more general, yeah? That the data is distributed as normal with the mean mu and the variance sigma squared. Yeah? So obviously, in real life, yeah, we observe different types of dependency structures, yeah, but we would like to see that the data is behaving normal. And of course, the question arises, what type of impact have different dependency structures that we see in the data on our empirical tests? And this is something that we would like to discuss in what follows. In what follows, we will discuss everything and use this simple model here, which is a linear equation, which is a single equation. Yeah? So our dependent variable is denoted as yt, which is typically the case. Then we have obviously here a linear relationship, so it's a linear model. So we have a constant term denoted as alpha. X1 is our first regressive variable, which is our first independent variable. We have x2, t, as our second independent variable. T denotes the time index, the time dimension, and we have here our x3t. Let's just add it here. Our x 3t, and then we have also our error term denoted as ut. Yeah? And we have also the parameters here, obviously. So yt is dependent on x1t, which is modeled by this beta 1. This beta 1. Beta 1 gives us the exposure of our dependent variable, with respect to the first regressor. Now, so this is a very general model, obviously, which you can use in many different contexts of empirical research. If we have, for instance, if we consider a marketing context, you might have here on the as dependent variable yt the changes in profits of a company, and we might have here as our first regressor the changes in expenditure for marketing action number 1. Our second regressor could be the changes in expenditures for our marketing action number 2, and the third regressor could be then obviously the changes in expenditures for our marketing action number 3, right? So in finance, we operate often, or we typically use in different research settings the so-called Farmer and French 3-factor model, where basically the portfolio return, which is then our YT, our portfolio return in excess form. So we typically subtract the risk-free rate from our assets. So our excess portfolio return is depending on the market factor, which would be then the x1t in excess form, of course. The size factor would be then our x2t, and the value factor would be then our x3t. So this is a model, and it can be also, of course, expanded easily. You can have much more regressors here on the right-hand side, and so on and so forth. And the random component here is our ut. So we can have different settings, different models, obviously. So we can have panel regressions, we can have time series regressions, or cross-sectional regressions. So the idea and the assumptions for all of these models are the same. And that is what we would like to discuss here. We would like to discuss the assumptions for ordinary least squares estimation. So that's an estimation technique that is used for, as I just said, for panel regressions, for cross-sectional regressions, or time series regressions. So, and obviously we have certain assumptions, and I would recommend you to write this down, because in my course you have to make your notes. So you have to make your own notes, and you have to write your own formulary. So these assumptions obviously are very important for our statistical tests. So all of our empirical research, all of our empirical tests and statistical tests are based upon certain assumptions, which may be quite strict, as we will see. So the first assumption, they concern the specification of that model. So first of all, the first assumption is that our variables x1t, our regressors here, they concern obviously our regressors, that the regressors x1t, x2t, x3t, that they are relevant. So the question is, so what happens if we miss a relevant variable? So what you hear often in econometrics class or in statistics class, the so-called omitted variable problem. So if we miss out a variable that is relevant, in order to describe our independent variable, then we face a so-called omitted variable problem, or we have this omitted variable bias. This omitted variable problem. So, and what people usually do in order to address this issue, if you are not sure if you have included all variables that are relevant for your model, then you would build a bigger model. You would use all variables that you have at hand that might be relevant, add it to them, and you would then test basically these additional variables if they have a significant impact on your dependent variable. Yeah? So obviously, if we miss out important variables, yeah, our estimators are biased, yeah, so they are of little use or of no use actually. So this is an important issue that we have to address, and this is what you typically discuss in econometrics classes. Yeah. You usually build, obviously, the solution would be to build a big model and to perform f-tests or chi-square tests in order to investigate which variables are actually relevant for your problem. So the second assumption that we have here, it's also very important, that the link between your dependent variable y and the regressors here is linear. So, for instance, what could be, what we do not want to have is, let's say, we have here our xi variable, and we have here on the y-axis our yi variable. Yeah? So what we would like to see is that they are, let's say, we have here our data points, yeah, that they are behaving in a linear manner, yeah, like this, for instance. So what we do not want to see is that they are, let's say, increasing in a non-linear fashion. So if our data plot look like this, yeah, it's basically obviously exponentially increasing. Yeah, this is what we do not want to have. We want to have a linear relationship. Yeah? So we have to ensure that the link between our dependent variable and our independent variables here is linear. Yeah? So, and this is also an issue that you typically address or that you typically discuss in econometrics class. Yeah, what you will then hear is about the so-called reset tests. Yeah? They are called reset tests, and they usually involve some type of Taylor expansion. So this is also something that you typically discuss during econometrics classes or in statistics. So the third important assumption, yeah, in order to derive our statistical tests, are that the parameters here, beta 1, beta 2, and beta 3, that they are constant. Yeah? So what could be, let's say, again, we plot our xi. Here, it could be x1, x2, or x3. Just choose one of these. It's just for illustration. So what could be is, for instance, that we have, firstly, it looks like this. If we plot one of these variables, xi against yt, it could be we have first this kind of link, and then all of a sudden it could be, for these observations here, it could be all of a sudden that the link is different. Yeah? So what we see here is that there's obviously a break in the beta I. So the beta I here in this sample here, in the first sample, is obviously smaller than the beta I for the sample that follows. Yeah? So what we have here is a structural break in the parameters. Yeah? But what we want to have is that the parameters are, that the link is constant, right? This is what we would like to have. We would like to have this, a linear link here, or we want to have that there's no structural break in the point estimator. So, and this is also something that you typically discuss in econometrics class. So you typically use dummy variables or a dummy variable model, where you basically test, where you can test if there's a break in one of these parameters. This is also typically something that is addressed in econometrics. So while the first three assumptions are concerned with the model specification, the second class of assumptions are concerned with the error term ut. Yeah? So, and the first assumption here is that the expectation of our random component, of our error term ut, is 0 for all t is 1 until capital T. So what we do not want to have is, if we plot, again, let's plot our error term here. This is our time dimension now, and here we have our errors ut, plotted against time. Yeah? Let's say we have a time series. So what we want to have is that the error term is on 0, on expectation. So obviously this would be violated, this assumption, if we have measurement errors in our yt. Yeah? So we assume that we, in our model, in the derivation of our model, we assume that we do not have measurement errors in our dependent variable. Yeah? So, moreover, what we also assume is that the variance of our errors is the same, is sigma square for all of our observations. Yeah? So obviously what we do not want to have is, or what we do not want to see is in the data that the, for instance, that we discussed already in the beginning of the lecture, we don't want to have that all of a sudden the variance is changing. So what we have here is obviously a clustering in the volatility. So the variance in this point of time, in this time period, is obviously larger than the variance in the beginning of the sample, which is quite obvious. So if we have here, if we split the sample, we get this variance here, and if we split the sample again and we would estimate the variance for the model for this period here, obviously the variance is much higher for this part of the sample than for the first part. And this is what we do not want to have when deriving our statistical tests. We want to have that the variance is the same. So what we want to see is, let's take this away. So what we would like to see is that, let's plot again here on the x-axis the time dimension, and here we have the error term of our model. So what we want to have is that the variance is the same. It's a well-behaving process. That's what we would like to see. So the next assumption concerns the covariance. So the covariance between two errors here, let's say the covariance between ut and us should be 0 for all t unequal s. So obviously if t is equal to s, we are dealing with the variance, because the covariance between us and us is the variance. So, and we know already that the variance is the same for all of them. So the covariance is defined as only for if t is unequal to s. And so we want to have that there's no covariance between any of these random components. So this would be violated, obviously. How could it look like if this is not fulfilled? Let's again plot here on the t-axis, on the x-axis, the t dimension, and here we have our error terms. So what could be is, let's say we have here 3 observations that are here, and then all of a sudden an observation that is here somewhere, and then again we have here some observation, then the 4th observation is again. So what we have here, obviously, here's a sort of a correlation structure, because always the fourth error is always much higher than the previous 3 errors. So this is what we do not want to see, obviously. So the errors should be well behaving. Yeah? There should be no correlation structure in the error terms. So moreover, we have the what we also should mention is here that these assumptions, 2, 1, 2, 2, and 2, 3, they are also often referred to as white noise. So whenever you read in the literature about white noise process, it means obviously that these three assumptions here are taken into account. So that the expectation of the errors is 0, the variance is constant, and they are serially uncorrelated. So the third specification, or the third assumptions, are concerned with the specification of the regressors. So what we also assume in deriving our statistical tests is that our regressors are exogenous. So that means that they are not random, so they are predetermined. And this is obviously only for didactic purposes, because obviously what we see is also random, but what we will see is that when we derive our estimators and our corresponding statistical tests, that this assumption actually does not matter so much, or it depends on the context. But for our purpose, this is not a problem. But if they are exogenous, what does it mean? So it means obviously that the covariance between our regressor x1t and ut is 0, because the only random part here is obviously this ut. So if we have this assumption, this is satisfied. So it also means that the covariance between the second regressor, of course, and our error term is 0. And finally, the covariance between the third regressor and our random component is also 0. So this is an important assumption, as we will see when we derive our models. So the final assumption that we have is that there should be no perfect correlation between the regressors. So what does that mean? So it means that the correlation between x1 and x3, for instance, should be smaller than 1 and larger than -1. And in the same way, the correlation between the second regressor and our third regressor should be clearly smaller than below 1 and larger than -1. And the same obviously for the correlation between the regressor x2 and x1, it should be also in the interval between -1 and 1. And obviously it wouldn't make sense anyways if the correlation would be 1. It means that these two guys here are exactly the same. So, and this is obviously something that we do not allow for when deriving this model, because this would be, first of all, redundant, and second of all, we could not derive our point estimator. Respectively, we could not either derive the covariance matrix of our point estimator. So all of these assumptions here summarize what stands behind when we talk about ordinary least squares. And it doesn't matter if we talk about panel regressions, time series regressions, or cross-sectional regressions. So the assumption here, if we derive the statistical tests, they are based upon this framework here. So finally, as an additional assumption, yeah, we have concerning the second part here. Let's denote it as assumption 2, 4, and this is what we need obviously when we set up empirical tests or statistical tests, yeah, of that model. So we assume that our error term, yeah, ut, follows an independent identical distribution, and this distribution is normal, yeah, with zero mean and sigma square variance. Yeah? So this is an important assumption in order to derive the statistical tests. Yeah? So, and in this lecture, and what follows is that we will have a closer look on the second part here. Yeah? So we have a closer look on the assumptions concerning our errors. Yeah? So we will talk about, okay, what happens if we deviate from this assumption. Yeah? What happens if we allow for dependency structures in our error terms? What happens with our statistical tests? Yeah? And finally, we will also investigate, okay, what happens if we not only deviate from these assumptions here, yeah, but what happens if we deviate from the assumption of the normal distribution? What impact does that have on our statistical tests? Let us now next talk about our notation. Again, we consider this single equation model here, yeah, where our dependent variable yt is equal with alpha, which is our constant term, plus beta 1 times x1t, plus beta 2 times x2t, plus beta 3 times x3t, plus our random component ut. So let us now define matrices and vectors. Let's put all this data that we have for our dependent variable into a t/1 vector. We can stack it here. We have it here. So let's denote y as a t/1 vector. So the dimension of our vector is t/1. So we put in here the first component or the first observation of our dependent variable, second observation, third observation, until our last observation, capital T. So we have here a t/1 vector of the dependent variables. So we can also construct an X matrix, where we stack in basically all the corresponding regressors that we consider. We have here obviously a vector of ones, is in the first column of our X matrix, and this corresponds to the intercept term alpha, which we have here as well. So we have capital T ones here in the first column. So the second column we stack in the observations that we have for the first regressor. So the first observation is x11. The second observation is x21. So obviously we have here the index ij, ij, where I denotes the rows and j denotes the column. And we know that we have in the rows the time dimension, right? And in the j is the cross section of our regressors here. So we stack the observations into this column vector here. So the last observation is obviously the observation of time capital T for our first regressor, x capital T1. So we do the same for our second regressor, our x2t. We start with the first observation and we end here with our last observation at time capital T. The same we do for our last regressor, our x3t. So we stack all the vectors here, vector of ones, and the vectors of our regressors into a matrix X, capital X. Yeah? And the dimension is obviously capital T. Yeah? This is a capital T by 4 matrix. Yeah? And in general terms, if we have, let's say, capital K regressors, yeah, so it's basically then a T by K matrix, yeah, to make it more general. And in our case here, in this model, let's also construct a vector beta, a beta vector, and what put we in? Well, the beta vector obviously stacks all of the point estimates of our model into a K or a 4x1 vector. Yeah, this is a 4x1 vector, but in more general terms, yeah, if we have K regressors, this would be then a K by 1 vector. And finally, also our random vector, or our error term, yeah, is also a T by 1 vector. Yeah? So we can now translate our single equation model into matrix notation. Yeah? So we can transform this, or we can express this in matrix notation. Yeah? This is what follows here. So we have on the left-hand side our T by 1 vector of independent variables, or that captures the evolution of our independent variable. We have here the X matrix multiplied with the 4x1 vector of our point estimates, and then we add, of course, the corresponding residual or error term. And of course, if we can do this for the first guy here, so the first guy here, what is it? So it is obviously we take the first row here, multiply it with this guy here. So what comes out is we have to multiply this with this plus x11 plus beta 1 plus x12 times beta 2 plus x13 times beta 3. And we add the corresponding error term at time t is 1. Yeah? So we can read basically for every point in time, we can read from this matrix system the corresponding realization. Yeah? So we just wrote it here in more compact form. Yeah? So, and we can easily express it then, because we have defined what it is. So we can basically then express it simply as y, vector y, is equal with matrix capital X times beta plus u. So this expression here obviously describes our single equation model. And then what follows is that we will use this expression here. And now remember the dimension that we have defined here. And again, if we make it more general, our X matrix is then a T by K matrix. But in our special case, since we consider obviously 3 regressors and here the intercept term, we have obviously a T by 4 matrix. But have this in mind, and then what follows is that we will derive everything based upon this model. So what is OLS doing? Ordinary least squares. So, and in what follows is we will derive it step by step, because in my course it is important for me that you understand what's going on. It seems to be, for me, that some academic teachers, they take some sort of prestige in that students do not understand what's going on, but that's not me. In my course, in my lectures, it's important for me that you understand what's going on. So what's the idea of OLS, of ordinary least squares? So it's basically a minimization problem. So what you do is you want to minimize the squared residuals. Yeah, and we know our residual vector is a t by 1 vector, so we transpose this guy. U transposed U. Obviously, if you transpose a t by 1 vector, it becomes a 1 by t vector times a t by 1 vector. So what's here in is a scalar. So what's here, this is a 1 by 1 vector, which is a number. So we know that our model is y is equal with x times beta plus u. So knowing this, it follows that our vector u is simply given by y minus our regression matrix times the beta vector. Yeah? So we can plug in this expression in our minimization problem here. So what we have to do is we have to minimize, obviously, y minus x times beta transposed times y minus x times beta. Yeah. So let's multiply this out here. So what follows? So if we, first of all, we have to transpose what is here in the first parenthesis, right? So what comes out is, so we have to transpose y minus, and now we have to remember from matrix calculus, if we have a matrix product, let's call it A times B. A times B transposed, what is it? It's B transposed times A transposed, right? So we apply now this simple rule. So in what follows here, we have to transpose beta first, beta transposed X transposed, it's still in the parenthesis, times this guy here, y minus x times beta. So what we do have to do next, so we can multiply this out. We have to multiply y transposed times y, which is our first component here, y transposed y minus y transposed times x times beta. So it's y minus y transposed x times beta. So next we take the second guy in the first parenthesis, which is minus beta transposed x transposed times our vector y. So minus beta transposed x transposed times y. And finally, we multiply the second component, the second term in the first parenthesis, which is minus beta transpose x transposed with x times beta. And minus times minus obviously gets plus, so it's plus beta transposed x transposed x times beta. So now we have to remember y transposed. So let's take the dimension here of our term. So what's the dimension of the first term here? Y transposed y. So y, we know it's a t by 1 vector. If we transpose it, it's a 1 by t vector. So what's here is a scalar. It's a number. 1 times t times t times 1 is 1 by 1, right? So that's a number. So this is a 1 by 1. Again, y transpose is 1 by t. 1 by t times, what is x? X has a dimension t by k, and beta is k by 1. So what is here is also, it's a 1 by 1, it's a number. Beta transposed is 1 by k, x transposed is k by t, and y is t by 1. So what is here is also, it's a scalar, it's a 1 by 1. And the same is true here, obviously. Beta transpose is 1 by k times x transpose is k by t times t by k times k by 1. So here, what we have here is also a number. So what we have here yeah, is 1 by 1. So it's a number. Yeah? But this number, obviously, is dependent. Yeah? So we are interested in the beta. Yeah? The beta that minimizes the squared residuals, the sum of squared residuals. So because these are scalars, so we can simplify. So it's this. So we can basically express this guy as this guy. Yeah? It's the same number. Yeah? It's just transposed. So this we have to rewrite. Let's take the first term here. We just write it down: y transpose times y minus 2 times this guy here, because they are equivalent. Yeah? So we can write it. We can write both terms as beta transpose x transpose y. So y transpose y minus 2 times beta transpose x transpose y plus the last term, which is beta transpose times x transpose x times beta. So in order to minimize this term, yeah, let's minimize it. We have to take the derivative. We have to take the derivative of this term here with respect to beta. Yeah? So this is what we will do now. So let's take the derivative of what is here in parentheses with respect to beta. Yeah? So what's the derivative from y transpose y with respect to beta? So obviously there is no beta herein, so it's 0. So it's 0. So what's the derivative from the term minus 2 times beta transpose x transpose y? So the derivative is obviously minus 2 times x transposed y. So the beta disappears, right, if we take the derivative. So what's this expression here? This is also something that you learn in matrix calculus classes. Yeah? So if we take the derivative with respect to this guy here, yeah, we have 2 betas here. So it's plus 2 times x transposed x times beta. And now we have to put it equal to 0, yeah? Because we are interested in the beta. Now we have to put here a hat on, because now it's an estimated, it's the estimate. So what happens now, what we can do is, so first of all, obviously, we can take away this 2 here, because and we can take also away the 0 here. Let's take away this 2, because it's in both, obviously in both terms the same. So we can just take it away. So what do we have to do next? So we can put this guy here on the right hand side, and what remains on the left hand side is then obviously x transposed x times beta hat is equal to x transposed y. Okay? So in order to get to our beta hat, what do we have to do? So we have to get rid of this x transposed x, which is a matrix product. So what we know also from linear algebra is, if we have a matrix A, and we multiply it with the inverse, and it doesn't matter if we multiply it with the inverse from the left hand side or from the right hand side, but if we do that, what we get is the identity matrix. And what we also know is, any matrix that we multiply, let's multiply the identity matrix with the matrix B, any matrix that we multiply with the identity matrix is the same matrix. Yeah? So the identity matrix doesn't change anything. So we apply this rule here and multiply this expression here with the inverse of the matrix product X transposed X. So let's do that. So X transposed X inverted times X transposed X times beta hat is equal with X transposed X inverted times X transposed Y. Obviously, we have to do the same operation on both sides of the equation, right? So this guy here becomes the identity matrix, and this doesn't change anything because the identity matrix times beta hat is beta hat. So we can take this away, and what remains is our OLS point estimator beta hat. Yeah? This is the first important result. So, and we will come back to this throughout the course. Yeah? So what we also see from this expression here, so what's the random part here? So the random part obviously is y, our y, because our y is dependent on what is the error term here, and the error term is the random component. Yeah, this is according to our assumptions because we assume that our regressor matrix has exogenous, that is predetermined regressor. So the random component is here our error term. So we see that our point estimator, our beta hat, is dependent on a random component here by y. So if we can express this here as matrix C. Okay. So what is then? We can say that our beta hat is basically C times Y. What does that mean? It means that our point estimator beta hat is a linear function of Y, and Y is a function obviously of the error term. So beta hat is a linear function, so it's a linear estimator, it's a linear in Y. That's an important result, and we'll come back to that later. So let's move this equation up on the top of the whiteboard. So next you might wonder, okay, but what happens if our X of our regressor matrix is not random? Because obviously this is an unrealistic assumption. So let's say if X is random, we have to perform the minimization problem, or we can perform the minimization problem of Y, of U transposed U conditional on X. And what we'll find is that our beta hat conditional on X is the same. It's X transposed X inverted times X transposed Y. So obviously the end result does not change. So, and it is obviously important, this holds only if our X regressor matrix X and our error vector U are uncorrelated. So this is typically in our framework, that's not the problem. But it could be a problem if we have a dynamic model. If we have a model, for instance, let's say our yt is depending on a constant alpha plus beta 1 times x1t plus beta 2 times yt minus 1 plus ut. So you see, we have here a lag term from the left-hand side in our regressor set, our yt minus 1. So what's our yt minus 1 then? Well, it's alpha plus beta 1 x1 t minus 1 plus beta 2 times yt minus 2 plus ut minus 1. But now we can express our initial equation yt as alpha plus beta 1 x1t plus beta 2 times what we have here. Now we have to plug it in here. Plus ut. So what we see is that our regressor set, if we plug in the second equation here into the first equation, what we see is that our regressors are dependent on past error terms, which we have here. So and we can do it now iteratively many times. So what we see is that our regressor set is dependent on a set of past errors. So and that's problematic, because now our regressor set is obviously, there's a dependency structure between our regressors and the errors. So in this case, obviously, this assumption is not satisfied anymore, because we can only do this, or this is basically only applicable in cases where our regressor matrix is uncorrelated with our error term. And this is not satisfied in so-called dynamic models. And this is something that you often encounter in economics, but this is not something that we would like to discuss in our class. The next question that arises, or that we are interested in when it comes to empirical testing or statistical testing, is what are the properties of our point estimator? So what's the expectation? What is the expectation of our beta hat? So we know we can just plug it in here, the expectation of our x transposed x inverted times x transposed y. And we know that our y is nothing else but x times beta plus u. So we can plug it in here. Then we know that the expectation of beta hat becomes x transposed x inverted times x transposed, and now we have to replace, or we have to plug in what is on the right hand side of the equation here, and so we have here then x times beta plus u. What we can do next is we can multiply out here what is in the parentheses here. So we have to multiply the term that is before the parentheses with each element here in the parentheses. So what we get out is then that it's then the expectation of x transposed x inverted times x transposed this first term. So it's then x transposed x inverted times x transposed x times beta plus x transposed x inverted x transposed x inverted times x transposed times u. So, and we have seen this before. So what we have here is obviously a matrix product x transposed x, and we multiply it with the same inverted, with the same matrix product but inverted. So what is here is the identity matrix. So the expectation of our beta hat is equal with the expectation of what? Of beta yeah, this becomes the identity matrix, so what remains is the beta plus the second guy here, plus X transposed X inverted X transposed times U. And we know that the expectation operator is a linear operator, so we can move it in the parentheses here. Yeah. So what follows is that what we have here on the right hand side becomes the expectation of beta plus the expectation of what is here on the remaining part, X transposed X inverted, X transposed U. So an important result, or an important intermediate result, what we have here is that this guy here, obviously, the expectation of beta is beta, because beta obviously is the parameter of the real parameters. These are no estimated parameters, these are real parameters. So the expectation of beta is beta. What we can do is, we can move this on the left-hand side and put it into the expectation operator again. So it's the expectation of beta hat minus beta is equal with this guy here. The expectation of X transposed X inverted X transposed U. So this is an important result, that we should bear in mind. So I will move it up here on the whiteboard. Because this is an important result that we will need later on. Let's move it here. So the expectation from beta hat minus beta is equal with the expectation of X transposed X inverted times X transposed U. Okay, let's go back to our derivation here. So we have seen that the expectation of beta hat is equal with beta and the expectation of the second guy here. So now the question is, what is the random part here? It's the U, right? So because we assume that our regressor matrix contains regressors that are exogenous. So we can move the expectation operator here before the U. So what we get is then, let's do that. So what we get is then the expectation of U times this guy here. So and what's the expectation of U? According to our assumptions, the expectation of U is 0. So this guy here is 0, and hence the expectation, everything times 0 becomes 0. So what is here is also 0. So now we have shown that the expectation of our point estimator beta hat, our OLS estimator, is equal with beta. So it gives us on expectation, the real parameter estimator, or it gives us the real parameters. So, and this result shows that beta hat, our OLS estimator, is unbiased. It's an unbiased estimator. And this is a very important finding. And obviously, our beta hat is unbiased, the only thing that we have to obviously account for is that we don't have any systematic errors in measuring y, yeah, as we discussed when we discussed our assumptions. So we only have to ensure is that the expectation of u is 0. Yeah? It doesn't matter what kind of dependency structure we have in the data, right? Yeah? So the only assumption that is necessary for showing that our beta hat is unbiased is that our random part here, our u, is on expectation 0. So let's take this away. So we have to remember now, so what can happen? So what's the expectation then of our beta hat conditional on x? Yeah? Because once we deviate from our strict assumption that our regressors are exogenous, yeah, they can be also random, but in case they are uncorrelated, yeah, if our regressor matrix X is uncorrelated with U, so what we can do is, so what follows is that the term, our equation becomes then, it's still beta plus the expectation of X transposed X inverted times X transposed times U. So now you might remember what we could do earlier is we could, because this guy here was not random and our U was the only random part here, we could move this expectation operator in the parentheses, yeah, in front of the U, and that's why everything became 0. But what happens here, if our regressor matrix is independent from, or it's uncorrelated with U, yeah, or if this is random, we cannot do this anymore, basically. But there's one exception. If our regressor matrix is uncorrelated with U, yeah, we can rewrite this as beta plus expectation from X transposed X inverted times X transposed times the expectation from U. So we have to take the expectation from this guy here as well, because this is not random anymore. Yeah? If we neglect the assumption of strict exogeneity. But if they are uncorrelated, yeah, this is what we face in our model setup, then obviously we have to take the expectation from both random variables, yeah, from both random components here, and we can move the expectation operator in any ways. Yeah? And since this guy here is 0, yeah, it doesn't matter what's the expectation of that guy here, yeah, because everything that you multiply with 0 becomes 0, and our OLS estimator conditional on X is also unbiased. Yeah? It's beta. So there's also a very important result. So it doesn't matter if X is random or not, as long as we ensure, or as long as it's satisfied that the regressor matrix, yeah, is uncorrelated with the error term, yeah, then we have the same result. Yeah. Our OLS estimate for beta hat is unbiased. But what do we know? But what do we need for statistical tests next? Yeah. So obviously, yeah, this brings us to the covariance matrix of beta hat. And this is what we will have a look at now. Yeah? What's the covariance matrix of our point estimator beta hat? So the covariance of beta hat is obviously defined as the expectation of beta hat minus beta times beta hat minus beta transposed. Yeah. And this is so because the expectation, this is what we know from our previous result, yeah, the expectation of beta hat is beta. Yeah? That's why we can already plug in this result here. Otherwise, we would have beta hat minus the expectation from beta hat, yeah, times beta hat minus the expectation of beta hat transposed. But since we know again that the expectation of beta hat is beta, we can just plug in beta here. And now we make use of our intermediate result from the previous analysis, yeah, when we had a look on the properties of the point estimator. So we know, yeah, that beta hat minus beta, yeah, is this guy here, it's this expression. Yeah. So we can use this intermediate result and just plug it in here. Yeah. We plug it in here, yeah, and we plug it in here transposed. And again, what do we have here actually? So here we know that beta hat is a 4x1 vector, or a k/1 vector to make it more general. So it's a k/1 vector times a k/1 vector transpose, which is 1 by k. So what comes out here needs to have the dimension k by k. It's a k by k matrix. Yeah. And you know from statistics classes, yeah, that the covariance of, let's say, xt and yt, yeah, if we take the sample covariance, how is it defined? So it's the sum from t is 1 to capital T, yeah, of what xt minus x bar, which is the expectation, it's the sort of sample average if we take the counterpart, the sample counterpart, times yt minus y bar. Yeah. So that's basically the counterpart here, yeah, because now we have a vector, a random vector, yeah, and this sum sign here is obviously replaced by the expectation operator. Yeah. So what we have here is the vector counterpart of this expression here. This is basically how you can think of it. So again, what do we have to do? Let's plug in what it is. So the covariance of beta hat is then the expectation of this guy here. Yeah, we just put it in here, and it's x transposed x inverted x transposed u times the same thing transposed. So x transposed x inverted x transposed u, yeah, and we have to transpose this guy. So let's now, we can leave it as it is here. So that's our x transposed x inverted x transposed u. And what happens here? So we now remember that the last component, if we have a parenthesis and we transpose what is in the parenthesis, we have to change the order. So our u comes now first, and it's transposed, times the second component here, which is x transposed. If we transpose x, so we know from linear algebra, a matrix A transpose transpose is the matrix A. Yeah, if we apply this rule here, so what comes here is X, obviously, because X transpose X is X, and we have to change the order, so the second element becomes here, and the order becomes the second element also here, because we have three elements. Yeah, obviously, the third element becomes the first, second is still the second, and the first one becomes the third. And what we also know here, this guy here, if we X transposed X inverted transposed is the same. This guy here remains the same. So now we have done what we are supposed to do. We have now this large expression here, and now we have to figure out what it is. But first, let's move this equation to the top. So now we have moved the equation up here, and the covariance of our beta hat is equal with the expectation of this term. Yeah? X transpose X inverted, X transpose times U prime times X transpose X inverted. So what's the random part here again? So the random part is here in the middle, so it's the U times U transposed. So U is a t by 1 vector times itself transposed. Yeah? So what we have here in the middle is a t by t matrix, right? So the question arises, so what's the expectation from U times U transposed? So that's obviously the interesting part here. Yeah? So that's the random part, so we would move the expectation operator in, and we're interested in the expectation of U times U prime. So now we have to think about what it is. So our U is a t by 1 vector. It's with U1, U2, U3 until UT times itself transposed, which becomes a row vector with U1, U2, U3, and so on until U capital T. So if you multiply this out, we have to multiply this guy with this guy. So what comes here is obviously U1 squared. Next we have to multiply with this guy with the second guy, which becomes our element, the second element in the first row, and this is then our U1 times U2. Then we have U1 times U3, U1 times U3, and so on and so forth until we end up with U1 times U capital T. And if we do this for all, we will see that we have here then our U2 times U1, and the second element on the main diagonal is our U2 squared. So the last element here obviously will be UT times U1. The third element on the main diagonal is then obviously our U3 squared, and so on. So the last element on the main diagonal is our U capital T squared. So that's basically the matrix if we have multiplied this one out. And now the question arises, so we have to take the expectation of each element here in this matrix. So let's take this away. So the question arises, so what's the expectation here? What's the expectation of the first element here on the main diagonal, the expectation of U1 squared? What is it? So we can rewrite it as the expectation of U1 minus the expectation of U1 and square it. What's that guy? So we know the expectation of U1 is what? It's 0. Because according to our assumptions, UT follows is identically independently distributed as normal with zero mean and sigma square variance. Yeah, this is our assumption. Yeah, remember we discussed this in the beginning. Yeah, this is the assumption. So that means, yeah, because this is zero, yeah, these two sides, or the right hand side, is equivalent with what is on the left hand side. So the expectation of u1 squared is the same as the expectation from u1 minus the expectation of u1, which is 0. Yeah? And we can always augment or expand with 0, yeah, squared. And this is nothing else than the variance. Yeah? That's the variance of our ut, and this is sigma squared. So the first element here, obviously, on the main diagonal is sigma squared. Sigma squared. Yeah? And if we do the same thing for the second element on the main diagonal, yeah, ut, u2t, or u2 squared, yeah, if we just exchange it here with, take the second guy, so we just have to replace it with 2, yeah, and it's the variance of the second guy, yeah, and because all of them have the same variance, yeah, it's also sigma squared, yeah, because we assume, according to our assumptions, the variance is the same for all t. They all have the same variance. So what is here on the main diagonal, obviously, is sigma squared. Yeah, we can do this for all the others as well. Yeah. So what remains on the main diagonal is sigma squared. Yeah. It's obvious. Yeah. Again, why is it like that? Because we assume that the random variables, yeah, they follow the same distribution, and all of them have a variance of sigma squared. Well, what about the second guy here? U1, what's the expectation of U1 times U2? Well, what we can do is we can do the same trick. We can expand it. So we can expand it by 0. So it's U1 minus the expectation from U1 times U2 minus the expectation from U2. So we know the expectation from U1 is the same like the expectation from U2, which is 0. Yeah. So this is 0, so we can always expand with 0. And what's this expression here? That's the formula for the covariance. Yeah? So that's the covariance of U1 and U2. And we know that the covariance between U1 and U2, what's that? That's 0. Because according to our assumptions, yeah, we have a normal distribution which is identically and independently distributed, yeah, for all t. So this is, again, if you now scroll back, think about our assumptions, yeah, concerning the error term. So this was one of our core assumptions, yeah, that the covariance, yeah, between us and ut is 0 for all s unequal t. Yeah? So what is here? That's 0. And if we do the same operation for all the other elements, we will see, what we will see is that everything above and below the main diagonal is 0. So let's take this away. So obviously the expectation of here, of u times u transposed, is this guy here. Yeah? So we have a matrix that has on the main diagonal sigma squared, and above and below the main diagonal always zeros. Everywhere are zeros. And that's a t by t matrix. Yeah? The dimension is t by t. So what can we do? So we know that sigma square, that's a number. Yeah? That's the variance of our random variable. So we can, because it's the same, we can just move it outside the matrix. We can move the sigma square outside the matrix, write it here in front of the matrix, and what remains here on the main diagonal are obviously ones. Yeah, so that's equivalent. So what's that guy here? That's the identity matrix of dimension t by t. Yeah. So since we know that, what we can do next is, we have to remove this now. What we know, this guy here, we can rewrite it as sigma square, the identity matrix of dimension t. Yeah. So what happens now? So let's plug in our result in this equation. So the covariance of beta hat is then the expectation of x transposed x inverted times x transposed times sigma square, the identity matrix, times x times x transposed x inverted. So that's the number. We can put this outside the parentheses. So it's then sigma square times what? Times x transposed x inverted times x transposed times the identity matrix times x transposed x inverted. So what's the identity matrix times x? That's x, so the identity matrix obviously doesn't change anything here. We can just move it back. So what do we have here? So it's x transposed x times itself inverted. And we know what is this? It's the same as A times A inverted, and that's the identity matrix. So what comes out here is the identity matrix as well. And what we know is if you multiply something with an identity matrix, it remains the same matrix. So what happens here is, if you multiply this out, what remains is sigma square times x transposed x inverted. And that's the covariance matrix of our beta hat. So that's a very important result. So based upon our assumptions, if our assumptions hold, so the covariance matrix of our point estimator beta hat, which is necessary to estimate the t-statistics, what we get out is that the covariance matrix of our point estimator breaks down to sigma square, which is the residual variance, times the regressor matrix of our regressor sets, transpose times itself inverted. Yeah. So, and now the question arises, so it's now important to bear in mind that this only holds if our assumptions are satisfied. Only if our assumptions are satisfied, we can obviously estimate the covariance matrix like this guy and use the standard t-statistics. So, and what is this? What is that? So that's a number, yeah, our residual variance, that's a number, yeah. And what do we have here? That's a t by k matrix transposed. So that's k by t times t by k. This is k by k, yeah. A k by k matrix, yeah, inverted, multiplied with a number is still the k by k matrix, yeah. So obviously the dimension doesn't change. So what we have here is, that's a k by k matrix, and in our case, you remember we had obviously 4 regressors in our matrix. We had 3 variables, x1, x2, x3, and we had the constant. Yeah? So we had 4 regressors in our x matrix. So in our case, it's this guy here. Well, what comes out here is simply a matrix, which is, let's call it C, which the elements of this matrix are C, C11, C12, C13, C14. Yeah? Then we have C21, C22, C23, C24. Then we have C31, C32, C33, C34, C41, C42, C43, and C44. Yeah, this is what comes out if we do the matrix calculus. So, and what's that? What's our C11? Yeah. So our C11, this guy here, that's the variance of our alpha hat. Yeah. What's C22? The second element on the main diagonal. So that's the variance of our beta 1, right? So the third element on the main diagonal, that's the variance of the third parameter, of the second beta, which is the third parameter estimate. And the last one, this C44 on that matrix, is obviously the variance of beta hat 3, which is our fourth parameter estimate. Moreover, C1, what's that element? C12. So C12 in this matrix, that's the covariance between our alpha and beta 1. C13, what's that? It's easy now. It's obviously the covariance of our alpha and our beta hat 2. Yeah. And finally, our C14 would be then the covariance between our alpha and our beta hat 3. Yeah. And obviously, this variance, so this covariance matrix is symmetric. So what we have here, the element C21 would be the covariance between beta hat 1 and alpha, which is the same as the covariance between alpha and beta hat 1. Yeah, and so on and so forth. So we can go through the covariance matrix here. It's a symmetric matrix, yeah, that has on the main diagonal, yeah, the variances of our point estimators, and above and below the main diagonal, obviously we have the covariances between our point estimators. So, and the question arises, well, how do we compute now our t-statistics? Yeah, for instance, for our alpha, well, we have to obviously grab the alpha from our point estimator beta hat. Yeah, take the alpha from the vector and divide it by the square root of that guy here, of C11. So that's the t-statistic for our alpha hat. Yeah? That's how you would do it. And in the same way, because obviously C11 is the variance, yeah, of our alpha hat. So how do we get the t-statistic for the beta 1? So it's obviously the same thing. Yeah, we would go to our point estimator. We would get the second element from the point estimator beta hat, and the second element is our beta hat 1, and you would divide it by the corresponding element, square root of the element on the covariance matrix, which is obviously here the element C22. Yeah, this is the t-statistic for our beta hat 1. And in the same manner, yeah, we would estimate the t-statistics for all of the other point estimators. Yeah. And obviously, yeah, it is assumed here that the random variables are normally distributed, which in turn means obviously that our point estimators are also normally distributed. So what you would do then is you would compare the point estimators or the t-statistics with the normal distribution with the critical values. Yeah. We have usually 1.96 and minus 1.96 as the critical values for the normal distribution, because we know that above 1.96 are 2.5% of the probability mass, and below minus 1.96%, below minus 1.96 are also 2.5% of the probability. So whenever our t-statistic has a value that is either above 1.96 or below minus 1.96, we would conclude that our point estimator is statistically significant given we have a 5% significance level. Yeah. So if we would test, let's say we want to test our null hypothesis, yeah, that our alpha is zero, and the alternative hypothesis that our alpha is unequal to 0. This is the standard test, and given you have a significance level of 5%, yeah, you would compute the t-statistic, yeah, for the alpha, and you would compare the t-statistic, yeah, with the critical values of the normal distribution. And whenever this t-statistic is above 1.96 or below minus 1.96, you would conclude that you would reject the null hypothesis, yeah, because the t-statistic indicated that this point estimator is significant on the 5% level. Yeah. So this is basically how you would implement a t-test based upon your results. And in the same manner, you could test the other point estimators for significance. So the question arises, what test do we have to implement if we have a combined hypothesis?